Hello, good evening, everyone, and welcome to another session of the Maker class. Today we'll be covering, or we'll be continuing from where we left off the last time on conditional probabilities. So, fasten your seatbelts and ready for the session. Please, to the other coordinators, could you please help me prompt the people in the group that we are beginning right now? So they should join us now so that we go together. Okay. So before they join us, let's do a quick recap on our last lesson. And as we do that, we'll be perhaps working some examples and also make the concepts that we studied in the previous lessons even clearer. All right. So introduction to conditional probability and understanding how one event can affect another. All right, so go. Okay. So here are some of the things that we've discussed so far. Probability describes the chance or likelihood that a particular event will happen. And we have an event. An event is a specific outcome or a set of outcomes from experiments or an experiment or a situation. We have the conditional or dependent events. And this is what happens when one event probability relies on another's prior occurrence. So it means in order for one to happen, we calculate it depending on the fact that the other one has already happened. And then an outcome is a possible result of an experiment or an action. Okay. So now what is probability? As we discussed earlier, it helps us measure how likely something is to happen. For example, the chance that it will rain tomorrow, or the chance of drawing a red card from a deck of cards. We can use numbers between 0, stating impossible probabilities, and 1, so saying it's certain to describe probability. Events, outcomes, and sample space. Breaking it down, we say an event in tossing a coin is either you get a head or a tail. The outcome is the actual result, for example, a head or a tail, and then the sample space is the set of all possible results, in this case, heads, tails. Understanding these terms help us talk clearly about probability. All right. When events depend on each other, real-life connections sometimes the chance of sometimes the chance of something happening depends on something else. For example, the chance of being late to work if it is raining. So now this time we are not just measuring the probability of you being late to work, but we are doing it how the chance of you being late to work provided that it is raining. So we are looking at two events. One is you being late to work depending on the fact that it was raining. The next one is the chance of picking a mango from a basket after one has already been removed. These are situations where conditional probability is used. So now, what's a conditional probability? The last time we met, we looked at the formula. The probability is written as conditional probability of an event A given that B, and it's read as we have stated, A given that B. The event that is written over here, the B, the slash B, is the preconditioned event. So it's the event that must happen first, and then depending on that, we check just how likely it is for the other to happen. It says that the conditional probability is written as P of A given B, which means the probability of an event happening, an event A happening, given that event B has already happened. For example, the probability of being late, given that it is raining. So then the probability of being late, given that it is raining, it means that the rain has already happened. We are calculating the probability of you being late as it is raining. So the rain is a pre-existing condition. It's not like it has already happened, but it should be the condition that should happen, and then the next one be the one that we are calculating. So now it means the chance of being late given that it is raining. Now it can be written as P of A given B. The formula for working out this probability is equal to probability of A and B happening all over B. We explained this the last time as B becomes your new sample space. So the probability of B becomes your new sample space. And inside that sample space, the people, or the particular group of people we'll be looking at are those who are members of B and at the same time, members of A. So we are looking at a classroom. We are looking at the number of people wearing, the number of boys wearing red shirts. And we want to calculate the probability of picking a boy who is wearing a red shirt. What this means is that we are going to have to go into the total number of people wearing red shirts, then separate the number of them who are boys. So the number who are boys become the boys wearing red shirts. In other words, let's say boys is B and red shirts is R, B intersection R. Then the probability is going to be the number of B's who are wearing R, that's B intersection R, over the total number of people who are wearing red shirts, which will be probability of R. So that is basically what the formula implies. So remember, always find the intersection divided by the precondition or the pre-existing condition. And that is everything. Calculating conditional probabilities. We also looked at this the last time we met. It says that decide what A and B are in your situation. So for example, picking a red sweet first, or B first sweet was coming. Let me move this thing. Okay, so it says picking a red sweet, or B first sweet was blue. To count the given outcomes or the possible outcomes. So work out how many outcomes fit both events and show how many fit just B. Divide to find the probability, and the conditional probability is equal to outcomes for both A and B divided by outcomes for B, where B is the pre-existing condition or the condition that we are describing using the if. All right, the if condition. We proceed. All right, looks like, let me clear this, sorry. I was doing this so that we will be able to work it faster when it's time for us, but it's covering space and I don't want that. So let's clean it. It will waste our time when we are working, but then still we can do that. And we can do it ourselves, as I said. All right. Let's look at an example. So the last time we met, we discussed how to even do workings for this. This example, I have already stated the answer so that we can know what we are working towards, right? So this one says that a die is rolled. We should find the probability that the outcome is even, given that it is greater than 3. So we are finding the probability that it is even, given that it is greater than 3. So what we use in the pre-existing condition here is, the pre-existing condition is the fact that it is greater than 3. So we are looking for the chance of rolling an even number that is greater than 3. What this means is, according to what we have seen so far, even this one, the question states how the formula should be written. Let's say we define the even numbers as E, and then so E like this, and then we define the values greater than 3 as G. On the face of a die, the even numbers are 2, 4, and 6. Am I right? Yes. And then all the values greater than 3 on the face of a die are what? 4, 5, and 6. So knowing these two different sets, we can now write our formula. The formula says that the probability of getting an even number plus getting an E, given it is greater than 3, which I'm representing with a G, is going to be equal to, so I've stated the formula on every page so that it will be easier for us to refer to it and then draw them out. So probability of E given B is going to be equal to the probability of the intersection of E and G. So in other words, the even numbers that are also greater than 3. all divided by the sample space, which will be every single number that is greater than 3. So the probability of getting a number greater than 3, the probability of G, like this. So now let's pull out a few things. First off, we need to identify the probability of E intersection G. So these are the values we need. We just need E intersection G and we need probability of G. So now let's come to the two sets here. On the face of a die, remember that the total number of outcomes is always 6, right? On a fair die, and that's what we are dealing with here. What is the intersection here? Or how many intersections do we have here? Remember that the possible outcomes in a given die are 1, 2, 3, 4, 5, and 6. So now, out of these 6, how many are intersections of E and G? So you may unmute, you may raise your hand and then walk us through that quickly. Out of these 6, how many are intersections in sets E and G? Yes, someone wanted to attempt. Please, who is it? You may speak.
Okay, the intersection of E and G is 4 and 6.
4 and 6. Okay, so he says 4. That's
that
this
would
guy
be,
right here. Yes,
that
sir.
would be 2 over 6.
That would be 2 out of 6.
And another way you can say 1 over 3.
Another, okay, good. So when simplified, that's 1 over 3. Excellent. This is Mr.
Kayun.
Sakayun. Thank you for your contribution. So then he says that the values that are in E as well as in G are the values 4, as you can see here, and also 6. And that's exactly 2 outcomes. Because 4 and 6 in the sample space, that's 2 outcomes. Over the total number of outcomes, that's 6. And he says when simplified, can even be rewritten as 1 over 3. So either 2 over 6 or 1 over 3. So let's go with 1 over 3. It's easier to handle. So 1 over 3. So now, we know what the probability of intersection G is. Now, the next parameter we need is the probability of G. So what would the probability of G be? In other words, the probability of getting a number greater than 3. So according to the data we have here, the numbers greater than 3 are 4, 5, 6, and that's exactly 3 of them, right? So on the face of the die, there are 3 numbers that are greater than 3. So that's going to be 3 out of the total, which is 6. And that interprets towards 1 over 2. The probability of getting a number greater than 3 is 1 over 2, like so. Good. So now let's plug these values into the formula. So probability of E intersection G, that's what you see over here, divided by probability of G. So E intersection G is, we know that to be 1 out of 3. And then we divide that by the probability of G, which is 1 over 2. So if you have a calculator, you can punch it. Or while you do that, I'll also be working it. 1 over 3 divisions convert to multiplications when you are working fractions. So that's 2 over 1, right? 1 multiplies 2, and then that gives us 2. And then 3 multiplies 1, and that gives us 3. And that brings us to the answer that we had right here, 2 over 3. So this is basically what conditional probabilities are about. Calculating one event pertaining that one happens first. So today, I have thought through the questions and quizzes we've done so far. I took some questions in there. I toned them down a little. That's where about conditional probabilities, tone them down and arrange them in levels so that as we progress further, then the complexity gets higher. We are going to work through all those examples, and by the end of it all, we will say we have fully covered conditional probability so that we can progress further to total probability rule. Then we do Bayes' theorem. And then after doing that, perhaps next time we meet, we can look at the functions. Slowly, we are advancing towards the end of statistics, by the way. There is much to do, but then with the time we have, perhaps it's doable. Okay, are there any questions pertaining to what we just did before we move on to the next example? Okay, let's proceed. So another one says a card is drawn from a standard deck. Find the probability that it's a heart, given that it's red. A card is drawn from a standard deck. Find the probability that it's a heart, given that it is red. Now, questions like this require you to know some basic information about most of the things that are used for probability. Like you need to know basic information about a Ludo die, a coin, a deck of cards. Now, if you are familiar with playing cards, this should not be trouble to you. But to those of us who are new to the game, here's basically how this works. In a standard deck of cards, there are four different types of cards. And these four cards, there are the hearts, diamonds, spades, and then what do we call it? Oh my God. Heart, diamond, spades. Hey, it's been a while. Is it club? No, I think club is the spade. Someone should remind me. Yɛwɔ yet, yɛwɔ spa, yɛwɔ kule, and yɛwɔ kalo. Yeah, club is club, all right, yeah. So then hearts, diamond, spade, and then club. Each of them has exactly 13 cards. So there are 13 hearts, 13 diamonds, 13 spades, 13 clubs. And then of these different groups, exactly two are red. So then the hearts are all red, and then the diamonds are also all red. Keep that in mind, okay? So then we have 26 red cards in total, 13 of which are hearts, 13 of which are diamonds. And then we have the remaining cards that are not red and are all black. So now this question says that if we take the standard deck of cards, for standard deck of cards, let's take the probability, let's find the probability that the card we pick is going to be hearts, given that it is red. So what are the parameters we need for this? So let's write reds as that R. So the number of red cards there are is I mentioned 26. That's 13 hearts, 13 diamonds. And then the number of hearts we mentioned right now, that's 13. So then given this information, you know that we will need the probability of heart intersection red. So we'll need probability of H intersection R. So we have to find that. And remember that the total number of cards is always 52. So then to find H intersection R, we first have to probability of H given R, we first have to know H intersection R. So H intersection R is going to be how many cards are red and at the same time hearts, or how many cards are hearts and at the same time red. Think of this for a second. There are 26 red cards. Of those red cards, 13 are hearts, 13 are reds. Oh, sorry, 13 are diamonds. Now, if I ask you, how many of them are reds at the same time hearts? What is your answer going to be? How many of them are hearts and at the same time red? Or how many of them are red and at the same time hearts?
Let me try.
Yes, sir.
This is 1/2.
It's 1/2. And then please, what brought you to this?
Because you said that there are 13, right? So
Exactly.
if you divide 13 by 26, you finally get 1/2.
Okay, so what he is implying is that since all the hearts are automatically red, then the number of red cards that are also hearts is the exact number of hearts that are there, which is 13. So the probability of taking a red card that is also a heart is going to be the number of red cards that we know that are also hearts at the same time. And that is 13 red cards. But then Mr. Okay, so to the one who answered right now, it is not going to be over 26. And here is the reason. We are looking at the whole card sets, not just the red cards, because it did say that we are trying to pick from the standard deck. So then it means that we are going to do the probability of picking a red card that is a heart. So red card and heart is here. Yes, it's true. That's true. The number of cards that are red and heart, that is exactly 13 out of the total number of cards there are, which is 52. Okay, so then the probability R intersection H that we'll need for the top of our formula, like this one right here, is going to be how many cards are red and at the same time hearts. That's 13 out of 52 cards. So we do that nicely. Finally, we divide this by the number of cards that are just red, right? That's the second part of the formula. So divided by probability of B. So this is our red, that's A intersection B, which is A, sorry, this is our hearts, that's A intersection B, which is our red, all divided by the probability of getting a red. So what's the probability of picking a red here? Is the number of reds over the total, which is 26, over the total, which is 52, like so. So then we have 13 over 52 divided by 26 over 52. So you can punch this on your calculator and give us the answer quickly, or I will be working it while you do that. So that's the same as 13 over 52 multiplied by 52 over 26. Remember, when you are doing this, you reciprocate. Your denominator and numerator swap places when you are converting your multiplication to addition. So over 26. So 52 crosses out 52. 13 goes into itself once, and 13 goes into 26 exactly twice. So 1 multiplies what's left here, and then it gives us 1. And then the denominators also multiply, and then it gives us exactly what? 2. So then our answer is 1 over 2, and that is what we have over here. So now, for the next example, before I do it, before we get to it, I'll ask, do you have any questions? All right. I like to believe that we understand the lesson so well that we deem the questions not necessary. So then, this next question is yours to work. Okay. I'm going to leave you. I'll allow you exactly, let's see, 3 minutes, yes. Or 5 minutes is better. So currently it is 7:27. When it is 7:32, I will stop you and then we look at the working together. It says a bag contains 4 green balls, 4 red, sorry, 3 green, and then 3 blue balls. One is drawn at random. Now, if it is known to not be green, find the probability that it is blue. So you're finding the probability that it is blue, given that it is not green. Probability that it is blue, given that it is not green. Let me help you define a few parameters so that it will make your working faster. So then let's write our blue as B, and then let's write our not green as we would have represented it in binary, what do we call it, Boolean logic. So yes, not green here. So then we are finding the probability that it is blue, given that it is not green. Okay, you can apply what we learned concerning the agents of probability and then the property 1 of probability that says that, you know what I'm saying, right? Yeah. So you can get to it and work. If you have any questions whatsoever while you work, just draw my attention and I'll attend to you quickly. While you do that, I'll be taking a little snack. Yeah.
Can I talk? Hello.
Yes, sir. Go ahead, please. You may speak.
To me, I got 3/10.
Okay, you scored 3/10. Okay, okay. So I believe this is Mr. Kayum. So Mr. Kayum has finished with the working and he scored 3/10. Remember, the answer that I highlighted might not be correct, so don't be deceived. Okay, Mr. Joshua. Mr. Joshua Anand, please, what was your answer?
I also had 3/10.
Okay. Mr. Joshua also had 3/10. Mr. Desmond. Mr. Desmond.
Yeah, I also had 3/10.
Hey, why is everybody getting 3/10? Okay. Is there another hand up? Okay, I like what's happening here. But we are working too fast, so I was going to take a snack. Okay. All right. Then let's see what the true working is and see if we really had to get 3/10 or if we have been misled by an old trick in the statistics books. All right. So according to the question, right, a bag contains 4 red. You can see over here. Let me use a different colored ink for this one, else it will be mixed up on our faces. Right. So then 4 red, 3 green, and 3 blue balls outlined here perfectly. One is drawn at random. If it is known to not be green, find the probability that it is blue. If it is known to not be green, find the probability that it is blue. So this means the formula will be probability of it being blue, given that it's not green. That will be probability of being blue and not green. So blue and not green, all divided by the probability of being not green or not being green. Not being green, like so. So let's plug in the numbers that are needed for this. First off, let's figure out what the probability of being blue and not green is. So then the number of balls that are blue is here, and it says there are 3 of them, this number right here. And then the number of balls that are blue and not green. So think of it. If they say we are finding the probability that a certain number is blue and not green, blue and not green, that would be the number of blue balls, right? Because we want something that is blue and at the same time not green. Remember, over here in the bag, the balls that are not green include the red balls and also the blue balls. They are the balls that are not green. But the question, we want an intersection of those. We want the numbers that are blue and at the same time not green. That means it doesn't apply to the reds. It only applies to the blue balls. So the blue intersection not green is going to be the number of blue balls that are not green, which is literally the number of blue balls, 3. And then over, so we are looking for a probability, right? So over total number of balls that are there. And that's what? 4 plus 3 is 7. 7 plus 3 is 10. So the number of balls that are blue and not green is 3/10. Now we divide that, that's our intersection. We divide that by the probability of finding a ball that is not green. So what's the probability of finding a ball that is not green? So the number of balls that are not green is going to be, so let's check the bag. Currently, we have 4 red and then we have 3 blues, right? So the number of balls that are not green is 4 plus 3, and that is 7. So the probability of taking a ball that is not green will be 7 over the total number of balls in the bag, which is 10, like so. So now punch this on the calculator and see what your final answer will be. And I'll be working it while I'm at it. So it's 3/10. And we rokoto it, we reciprocate. That's 10 out of 7. 10 crosses out 10. 3, 1, 3. And then 7, 1 is 7. So then the correct answer is actually 3/7. But I'm interested in the fact that we all got 3/10, right? So I want to hear how your working was done, and let's see if there is a little misunderstanding somewhere or if it was just an honest mistake.
Okay. What I did, then I got the 10 is, you see, not being green, I use the formula, the complement formula. 1 minus
Okay.
the probability of not green.
Okay.
So that's
So
my,
that
so
was
I go
one.
1
That was
minus
one.
1
Three
minus
over.
3 over 10.
Okay.
Mhm. So that's how I got the 3 over 10.
1 minus 3 over 10, right? And what does that give us? I think it gives us 7 over 10.
7 over 10.
Yes. So then
So
that's the probability of not being green, right? That's the value over here. Okay, 7 over 10.
7 over 10,
Yes.
right?
Yes.
So I as finding the, what do you call, the intersection of B,
Mm-hmm.
blue, and not
Yeah.
green.
Yeah.
So I just use the direct formula, which is you can use the multiplication sign, which is
Oh, okay.
probability of blue, which is 3 over 10 times 7 over 10, all divided by 7 over 10.
So your intersection, you did
Yeah,
it by doing 3 over 10 times 7 over 10, like
yeah,
this. Oh, okay, I
yeah.
see where the problem is coming from. So I believe this one will be something that will be reflecting directly from me, but not entirely because we did do independent events and dependent events. It is for independent events, right?
Okay.
It is for dependent events that multiplying these two things will give you an outcome that is equal to their intersection. It's for independent events that multiplying these two things will give you an outcome for their intersection, or like same as the intersection. But if you check these values well, once you pick out a red ball from the bag, it actually affects the probability of you picking a green ball. Even though you only picked out one red ball, initially without picking the red ball, the probability of picking a green ball would have been 3 out of 10. But once you take a red ball out, the probability of you picking a green ball becomes 3 over 9. And that is different from 3 out of 10. It means one probability affects the other. And since the probabilities have affected each other, we say they are dependent because the occurrence of one event influences the other. For dependent probabilities, the product of A and B is not necessarily their intersection. So this is why we learned independent events, and we went through all the trouble of learning that. It was just to show you the distinction between events that have a correlation and events that do not. So if the events are independent of each other, it means one occurring doesn't affect the other one in any way. For example, when we are tossing a Ludo die, right? Me tossing one particular value cannot affect my next toss. If the first one's outcome was 1 over 6, the second one's outcome is still going to be 1 over 6, unless I'm doing sums or something. So then these are the events that are independent, and they are the one whose intersection can be found by multiplying them. So then for these events here that we see, picking a red ball affects probability of picking a green ball. Picking a green ball affects probability of picking a blue ball. Picking a blue ball also affects probability of each and every one. In the sense that if I take one red ball, probability of picking a green ball changes from 3 over 10 to 3 over 9. If I pick one green ball too, probability of picking a red ball changes from 4 over 10 to 4 over 9 because I've reduced the number of balls. So they affect their probabilities. Therefore, you cannot calculate their intersection by multiplying them. Is this clear? Is it like, does this make sense?
Yeah, but
Yeah.
the question is like it's quite confusing because it is not like it's a discrete probability, but it's not like it's not clear. The what do you call it? The sample space is not clear
Oh,
like
the
that.
sample space is not clear. Oh,
Not-
okay.
Yeah, I don't really know how to find the not.
Intersection.
Yeah,
Oh,
it is.
okay. All right. So then let me walk you through that. Okay. So then I believe that is genuinely the problem here. So then I'll first have to commend your efforts because you all were actually on the right track, except that you were applying a rule that only works for independent events. But these events are dependent on each other. And this is why it's led you to this answer. So kind of it's my fault. I feel like I didn't stress on the fact that the multiplications will only go for independent events. All right. So now let's see how the values of not green and the rest are coming about. Okay.
Okay.
Yeah. So give me a second to prepare some room on my screen. This eraser is blue. Okay. So now let's find the values we need. First off, we are to find the probability of getting a ball that is blue. According to the question, there are 3 blue balls. So probability of finding a ball that is blue, that's P of B, is just going to be number of blue balls, which is 3, over the total number of balls, which is 10. So there's the probability of finding a blue ball. Now, we need to find the probability, because we need that a ball is not green. So then the probability that a ball is not green, we just go to the question and figure out how many balls are given that are not green. So that's just the red balls and then the blue balls. So that makes how many balls? 7 in total. Or you can use the complement formula and that will still give you 7 out of 10. I believe we saw that here, 7 over 10. Now, the intersection, since these two events are clearly dependent on each other, seeing as picking one red ball affects your chance of picking a green ball in the next trial, then we cannot say red intersection green is necessarily 4 over 10 times 3 over 10. We cannot say that. So the probability of getting the intersection, the probability of blue and not green, we can figure it out this way. So now, let's go into our bag. So I'll draw in our bag, we have red balls. So there is 1, 2, 3 red balls. And in the same bag, or 4 red balls, sorry, 4 red balls, 4. In the same bag, we have green balls. There is exactly 1, 2, 3 green balls. And then finally, there are 3 blue balls. That's 1, 2, 3 blue balls. Now, we want to find the intersection, the balls that are blue and at the same time not green. So then the ball must be blue. It must be blue and it must also not be green. So let's come to the bag here and check. So this is our bag. Let's take all the balls one by one. The ball must be blue and not green. Does this apply to this red ball? It doesn't, because it is neither blue. Even though it is not blue, even though it is not green, it is not blue either. But the condition was it must be blue and also be green. And also not be green. So it's not just that it says not blue. If it was blue or not green, then it will apply to the red guys. So since the red guys are, even though they are not green, they are not blue either, they are out of the problem here. If we come to this side too, the question says they must not be green. So they must be blue and also not green. So these guys are also out of it. That will mean that the only people that are blue and at the same time not green is these 3 balls right here, which also happen to be the exact 3 blue balls. Mr. Kayu, is this clear?
Mm, okay.
It's
Yeah, yeah.
not.
But I
Yeah.
think the question is saying that if it is known to be not green.
Yes. So then that condition is what we see here. Probability
Okay.
that you pick a blue ball, given that it is not green. And according
Okay.
to the formula, we have to find the number of balls that are blue and at the same time not green. That's the intersection. You remember the formula, right?
Okay. Okay. Yeah. Yeah. Yeah.
Yeah. So
Yeah.
the struggle we are doing right now is to find the number of balls that are blue and at the same time not green so that we can come and plug it into the formula up here. You see
Okay.
that?
Okay.
Exactly. So then, in order to do that, that's why we are going through all these troubles. So the number of balls that are blue and not green will be the three blue balls who are at the same time not green. So you see, it doesn't apply to the red balls, neither does it apply to the green balls. It only applies to the three blue balls. So then blue and not green is going to be 3 out of the total number of balls there, which is 10. And then you plug them into the formula, sorry. That's going to be probability of B and not green, that's the one over down here, divided by probability of being not green, that's the one up here. So
Okay.
divided by 7 over 10.
If
Yeah.
I may get like so the not green is only applying for the down there. Like
Yes.
not G
Not
is
green alone is the
applying
denominator.
down.
Yes, sir. Yeah.
Okay.
Yes, sir. Exactly that. However, the one at the top is strictly blue and not green. If it was
Yeah,
an independent probability one, then your formula of multiplying the two probabilities would have worked. But in this
yeah.
event where you can see that taking one ball affects the probability of picking the next one, do not apply such a formula.
Okay,
Okay, sir? All right.
okay,
So to all those who made your mistakes, I have now seen why you made the mistakes, and then it's partly my fault. So remember, this only applies to independent events, but for these events, they are dependent. So do not try that on them. They don't like that. Okay.
okay. Thank you.
Now let's move on to the next question. So we are making progress. So we see our mistakes, we work on them. Next time, we do not repeat them. Okay. So with this one, I was drawing a table, but then I have to go and grab some food. So this one says that two dice are rolled. Let me clear this table. The tough, painful thing is that I'll have to draw it again. Okay, bear with the table, please. Two dice are rolled. Okay, I'll show you an image. I actually prepared an image for this. I forgot how prepared I am. Okay, I'm coming. So let me clear the table from there so that you can see the question clearly. Oh, it has even cleaned the correction I made there. All right. There's a little typo in the question. It's fine. So here's the question. It says that two dice are rolled. Given that the sum is even, let's find the probability that the sum is 8. Two dice are rolled. So we roll a die and another die. The outcomes of the faces, we are saying that we are trying to find the probability that the numbers that popped up sum up to 8 upon rolling the two dice, given that it is even as well. This might not make, this might be hard to understand, but then let me show you an image to prove that. Oh, I'm coming. Yeah, okay, I think this is the right tab. Good. It led me to plenty places. Was I just find good? All right. So please, you can see this clearly, right? So now we are rolling a die. When we toss two dice, this is the first die, this is the second die. We are trying to find the outcomes that give us the sum of 8. So let's first write out what the formulas and what's not should be. Okay. Okay, let me switch from sharing this to sharing my whole screen. I think so that I can use notations on the screen. All right. So as I was saying, we are trying to find the probability that a ball and the sum is 8, given that it is an even number as well. So please, I started annotations. Does it cause any problems on your screen as we were experiencing the last time?
No, it's not doing anything in my screen.
All right. Thank you. Okay, so now we are trying to find the probability that the sum is an 8. Let's use E for that. Given that it is even, what should we use for the even? Let's use Z. Z is normally for real numbers, right? But so the probability that the sum is an 8, given that it is even. That's what I'm using Z for. So the parameters that we are going to need for this is the probability of picking the Z, right? That's an even number. And we are also going to need the probability of picking an 8, which happens to be an even number as well, Z. That's because the formula will be P of E intersection Z over P of Z. So let's come to all the values here. Of all the values here, you can see that the ones that can give us a sum of 8 is when we roll a 2 and then a 6. That gives us 8 right here. So that's 1, right? We are counting how many 8s we can get to. When we roll a 3 and a 5, that also gives us 8. That's 2. When we roll a 4 and a 4, that also gives us 8.
Please, you are rather underlining 10.
Yes, sir.
But you say
Come
8.
again. Yeah, you said I am
It's 8.
Underlining 10 instead of
8.
8.
Are you sure? It's 8, so.
It's 8.
Mr.
It's
Kayu,
8.
please, is everyone seeing it as a 10?
No, it's
It's
8.
8, eh? Mr. Kayu, I think your screen is glitching. Oh,
Actually.
oh, sorry. Sorry. Okay, so now let's count how many 8s we can get. So as you can see, the combinations are for 2 and then 6, 3 and 5, 4 and 4. If you do 5 and 3 too, it gives you an 8. And if you play 6 first and play a 2, it also gives you an 8. So then the probability of getting an 8, right, is what you can see over here. And there's exactly 1, 2, 3, 4, 5 out of the 36 outcomes here. So then the probability of getting an 8, probability of getting a sum of 8, or E, sorry, probability of getting a sum of E is equal to exactly 5 over 36 outcomes. This is not what we want, by the way, but we will use it, 5 over 36. Now, what we need is probability of getting an 8 that is also an even number. So 8 intersection even number. So now, let's go into the table and find the number of 8s that are even numbers. But think of it. 8 is always an even number, right? 8 is always an even number. So the probability of picking an 8 that is at the same time an even number is still the same as the probability of picking an 8. Does that make sense? It's just like in the case of the blue and red balls. Currently, these guys here are even numbers. 2 is an even number. 4 even numbers. 6s are also even numbers. 8s are also even numbers. 10s are also even numbers. And 12 is also an even number. But the condition wants us to find numbers that are even numbers and at the same time are also the number 8. The probability of getting an even number that is also 8 is just for this group of people. The rest of them, even though they are even numbers, they are not 8. So they do not fall into the class of intersections we are talking about. So the probability of finding an even number that is 8, in other words, probability of E intersection Z is these values here. So the number of sums that are even numbers and are also 8 is exactly 5 out of the total number of outcomes there are, which is 36. Is this clear? Hello, is
Can
this
you
clear?
no? Can you take it again, Charlie?
Okay, let me take it again. So now we are trying to find the formula that says the probability of E giving if 8 giving that it is even is the probability of finding even numbers that are at the same time probability of finding a sum of 8 that's at the same time an even number like this. And then we are dividing all of that by the probability of finding an even number, which is Z, like this. So then we have this is what we are trying to achieve. So we need to know what this is, and also we need to know what this is. So to find the probability of even numbers that are also 8, we come to our tosses. So now when we did the tosses, these are, after doing the tosses, right, you are just tossing 2 times. It could give you any of these outcomes. Remember, you could have tossed the 1 and a 1, a 2 and a 2, or also on to the last one. However, we are just interested in the probability of you tossing an 8. So the question, the formula says we should find the probability of getting an 8 that is also an even number. So let's first come to the table and see. Let's count how many values are 8 and at the same time even numbers. So let's see. 2 is an even number, but is 2 an 8? No. So it doesn't fall into that category, so we cannot count it. 4 is an even number. This is 4. All these 4s are even numbers, but are they 8s? No. So they also do not fall into that category. If we come to the next set of even numbers, is 6. 6 is an even number, but is it an 8? No. So it doesn't fall into that category. We come to the next even number, that is 8 itself. Is 8 an even number? Yes. And then is 8 an 8? Yes, it is an 8. So then this is what we will count first as the number of the number of digits or number of sums that are even numbers and at the same time 8. That's going to be 1, 2, 3, 4, 5 out of 36. Let's go further to the other even numbers and see if we can find more. So then we come to 10. 10 is an even number, but it's not an 8. We come to the last even number, that's 12. 12 is an even number, but it's not an 8. So it means the only group that satisfies being even numbers and being 8 are these groups of 8 right here. So the probability of being an even number intersection 8 is going to be the number of 8s, or the probability of picking an 8. And that's going to be 5 8s out of the total number of outcomes that there could be, which is 36. If you count all the outcomes there could be, you get 36. 6 here, 6 here, that's 36. So the probability of picking an even number that is also an 8 is 5 over 36. Please, is that understood?
It's clear now. But
All right.
I thought the outcome, like if you add the outcomes,
Yeah.
if they are even numbers and the final result is 8, I
Yeah.
thought, or you don't get me, like the
You
outcomes, like
broke off. You broke off for a second. Please come
6.
again. You
Yeah,
said you thought. All right.
if you add them, like 2 and 6, they are even
Yeah.
numbers, and their
Yeah.
total is
8. Yeah.
yeah. So I thought we are looking for that one.
So those additions you're talking about, those additions are what give us the numbers that we are seeing over here. So currently you can see that if we roll the first and we get a 1 and we roll the second, we get a 1. Combining that gives us the value down here too. If
Yeah.
the first row was a 1 and the second one was a 2, that gives us the value down here 3. So now we are saying that after you do all these rollings, right, how many of them will give you a sum that is 8? That's what we have found here. And out of those 8, how many are even numbers? So then it happens that every 8 is an even number. So then being an even number and an 8 is exactly the number of 8s there are. That's 5 8 out of the total number of outcomes, 36. And that's what brought us to the intersection here. All right. Thank you. Thank you for bringing out these questions, and they'll really help us as we go further so that we can point out all the small mistakes. All right. So now that settles that side. Now, what about the next side that says the probability of being an even number at all? So that's just going to be the number of even numbers over the total number of elements there, right? Or the total number of outcomes. So the number of even numbers, let's count. We have the 2. It's an even number, right? So that's 1 plus these 3 4s here. They're also even numbers. So 1, 2, 3, 4. Let me use this one so that we can easily follow. So then that is, the 2 is an even number. So that's 1 followed by 2, 3, 4. They're also even numbers. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 even numbers here out of our total 36. So then the probability of picking an even number is 18 out of 36 outcomes, which is the same as 1 over 2, since 18 goes into 36 2 times. So let's just use 18 over 36 for now. It will be simpler to simplify since we already have that here, 36. So now that we know the parameters we need, we know what our intersection is, and we know what our even number value is too, And then we can now plug them into the formula. That's it, the probability of the intersection over the probability of even numbers. So that's going to be 5 over 36 divided by the probability of picking an even number, which is also 18 over 36. So please punch it on your calculators quickly. Let's see what our answers will be. While you do that, I'll also be simplifying. So this is the same as 36 crosses out this, or if you do the Rokoto and you do it, you realize that that is how it happens. So you can cancel horizontally in divisions, and you are left with 5 divided by 18, which is literally 5 over 18, like so. So what this means is the probability of picking an 8, given that it's an even number, will be 5 over 18. That's what you're seeing here. So you see, the formula doesn't change. No matter what the question looks like, it doesn't change. Even though the questions have increased complexity starting from the first question all the way to this point, you realize that it has still been the same formula. We just find an intersection and divide this by the precondition. We find the intersection divided for the precondition. And this is literally all that conditional probabilities are about. Are we clear? So please, are there any questions that you have to ask before I move on to the next example, if there is any? Or I don't even know. I think perhaps we are almost done with this side of it. Okay, looks like there are no questions. So everybody is fine. Okay, so then the correct answer is 5 over 18. That's what we just solved to get, right? 5 over 18. I believe my annotations will be worrying your screen right now. So let me delete all of them. So our correct answer is here, 5 over 18. That's what you can see. 5 over 18 up here. And then it has been highlighted as well to be 5 over 18. All right. Let's continue. So now, this one. In a Ghanaian market, there are 10 ripe plantains and 5 unripe plantains in a basket. If a customer buys 1 ripe plantain, what is the probability that the next plantain chosen by another customer will also be ripe? For this one, you do not even need to go and then do the long calculation. Even if you do the long calculation, you still get the same answer. But then since we are going to be looking at objectives, I want to see perhaps questions like this might appear. Let's see how we can just solve them without even applying the formula. So some basic questions, you do not require the conditional probability formula to solve them. You can just look at them and then the answer appears. An example is this one. So it says in the Ghanaian market, there are 10 ripe plantains. 5 are unripe. So then there are 10 and 15 plantains in total. Keep that in mind. 10 are ripe, 5 are unripe. If a customer buys 1 ripe plantain, what is the probability that the next plantain chosen randomly by another customer will also be ripe? This is what it means. The first customer came and bought 1 ripe plantain, right? That reduces the number of plantains in the basket to 14. So if the next customer comes and they want to buy a plantain, what's the probability that the plantain they are going to buy is going to be ripe as well? It will now be the total number of ripe plantains which are left divided by the total number of plantains that are left. So then initially we started with 10 ripe plantains, right? And now someone has come to buy 1 away. So the number of plantains drops to 14 and the number of ripe ones will also drop towards 9. So the probability of the second person or the next person coming to buying a plantain that is ripe is going to be the number of 9 ripe plantains, which is 9, divided by the number of total plantains, which is 14. And that is your answer right here, 9 over 14. So for some dependent events like this one, the answer is clear as day once you look at it. In other questions, this might not apply, but if you even think about it critically, you can actually draw the conclusion from other questions too. All right. So this is 9 over 14, by the way. Are there any questions pertaining to this? In case you see simple questions like this, Charlie, no time to waste or anything. just consider the fact that one of the ripe plantains has been taken away. It's not like you're going to see a ripe plantain question, but if you see a question like this, one has been taken away, how many are left, divided by how many are left in total, then you're done. That's your probability. So this is also a dependent probability. We can apply the formula and we will still end up at 9/14.
Hello, Mr. Prince.
Yes,
Please, can
please.
you take it again? Like,
Oh, okay.
yeah.
All right. I'll take it again. Okay. So let me take it again.
Okay, thank you.
Right. Yes. So now we are at a marketplace, and then there are plantains in a basket. I'm going to use red to represent ripe plantains, and I'm going to use what? Yellow to represent unripe plantains. So now in the markets, we have 1, 2, 3, 4, hey, chill, 5, 6, 7, 8, 9, 10 ripe plantains being sold by a lady. And then she's also having unripe plantains coming. Yeah. Unripe plantains, she has 1, 2, 3, 4, 5. Now we are saying that what is the probability? So we are saying someone comes, a customer came, and then they said, antimetal plantain, mepe cocoa. And when the person reached into the basket, the person picked a plantain for them, that was cocoa. And then that means the person has taken away one of the red plantains. So the number of red plantains has reduced. And then in effect, it affects the total number of plantains as well. So we are asking you, if another person comes that they also want to buy plantain, and the lady just randomly reaches into the bag, what's the probability that the plantain she picks is also going to be ripe? That will be number of ripe plantains over total number of plantains, right? And divide that.
Hello?
Yeah. So that will be,
Yeah,
I'm
please, I
saying
can
that,
hear you.
yes, please. So I'm asking, if the first customer has already deleted one plantain, we are asking that if someone comes and they also want to buy plantain and the lady reaches into the bag and randomly pulls out a plantain, what is the probability that that plantain is ripe? Abis will be the number of ripe plantains here divided by the total number of plantains that we have, right?
Yes, please.
So the number of ripe plantains, since we had 10 and we've taken away 9, the new number of ripe plantains is what? 9. And then the
9.
total that used to be 14 has now been reduced to, the total that
Okay,
used to
so
be
it's
15
without a replacement.
without a replacement. Good. So then they
Okay,
said he
okay.
buys the plantain. Uh-huh. So when you buy it, it's gone. You didn't bring it back. Over the total number of plantains that is left, that will be the 9 ripe plantains plus the 5 unripe plantains, and that gives you 14. So the
14.
probability of the second person picking a ripe plantain is going to be 9 out of 14.
Okay.
So this is another way you can look at the probabilities, the dependent ones. In some simple questions, this is how you can do it. If the question confuses you too much, don't bother. Just go ahead and start applying the formula.
All right.
All right. But for
Thank
simple
you.
questions like this, just take it fast. Okay. So is that understood?
Yes, please. Thank
All
you.
right. All right. Thank you for listening. So let's proceed to the next example. So this one, you will need to use the probability formula, but if you think you can do it with your mind, even without using the formula, try doing that and then you might actually get the answer correct. So this one, there are no possible answers. It says a box contains 2 yellow, 3 brown, and 5 white stones. If a white stone has been picked, what is the probability that the next one picked is yellow? So this one, you can use the formula, but you can also apply what we just did and you can get the answer equally. So try doing it mentally before applying the formula and see. So there are 2 yellow, 3 brown, 5 white stones. A white stone has been picked out of the bag. It has not been replaced. What's the probability that the next one is yellow?
Please, so all the okay, so in you add all the balls, right?
Yes, all the
It will
stones.
give you 10.
That's 10 exactly.
Yeah.
Yes.
And you said a ball is picked randomly.
Yes, a stone is picked at random. And then they said it was white.
Okay, so it's going to be um 4. Hey, wait, where's the white?
So
Please
then
hold
take
on.
note.
I'll come again.
Oh, okay. We'll be waiting for you. So take
So
note, there
it's
are two
going
yellow
to be
balls. Yes,
it's going to be 4/10.
4/10. Okay, I like what's happening here. So Vida says it will be 4/10. Yes. Are there any more answers? So I think Vida is applying the mental strategy. Then she says it's going to be 4/10. So then there are two yellow stones, three brown stones, and five white stones. Now, Vida, I want you to remember one thing and reconsider your answer, okay? Remember
Okay.
that the number of balls in the bag is affected by all the number of yellows, brown, and the whites. This means if I take
Okay.
out a white stone, it reduces the total number of stones, right?
Yes.
So will the probability really be 4/10? And
Okay.
also,
So
it says that the probability that the next one is yellow. So we are dealing with yellow balls, okay? Yellow stones. Eh? Why are we talking about balls?
are we talking about white stones or yellow stones?
It says that you first pick the white stone. What is the probability that the next one is yellow?
Okay. So let me do
Yes,
this
please.
thing.
So reconsider, okay?
Yeah, yeah, yeah.
So to the others too, we are waiting for you. Okay, should I go ahead
Hello, Mr. Prince.
or we are still trying?
Hello, Mr. Prince.
Yes, sir.
Okay, so my analysis, you add the yellow balls, the brown balls,
Yes.
and then the white balls, which gives us 10.
Okay.
And then out of it, we are picking a white ball. That's 1. We are picking
Yes.
1 minus the 10, which will give us 9.
Okay. So the
So
total now
out,
becomes 9.
yes.
All
So
right.
out out of the 9, now we are we are the question said what is the probability the next 4 pick is
Oh,
yellow, right?
yes.
So now that we have gotten uh, the total probability to be 9, and then and then the next ball is yellow. So I think the total answer will be giving us the number of yellow. That's the 2 over the 9. That's the answer.
Exactly. And that is the exact answer, actually. Okay. So I believe for the first, Vida thought we were doing it for white balls. That's why she went for 4/10. And then her second mistake was not changing the denominator. But that aside, she had the right idea. But then this answer actually defines exactly what these things are about. So remember, taking away one white ball affects what the probability of yellow should have been. Initially, it should have been 2/10. But because we have removed one white ball, it affects the total number there. So they are dependent on each other. This changes the probability to total number of yellow balls, that's 2, over total number of balls left, that's 9. And that's exactly what we want. So now, if we use the formula, we will still arrive at the same answer, 2/9. So basically what we've just done is we have done all these things without having to go through the trouble of, applying the formula and blah, blah. And this is very important, seeing as we will be dealing with objective questions. So now with this, I would like to believe that we have understanding conditional probability will help you cover at least 5% of the objectives. Now, I believe the man will be using the conditional probabilities, but then he will be applying them more to Bayes' theorem and total probability rules and all that. So then for that reason, in our next meeting, we'll be accelerating straight into the total probability rule, then Bayes' theorem. So you come prepared with the knowledge of what we have learned today, so that it will not be like we have to go back to old things and or else the drawback will be it's a waste of time. That's all. Okay. All right. So thank you for contributing. Let's move on to the next example. It says that in a class of 12 women and 8 men, a woman is chosen for a task. What is the probability that the second person chosen is a man? So yes, let's do this mentally. A woman is chosen for a task at random. What's the probability that the second person chosen this time will be a man?
That is 8/11. 8/19.
8/19. Excellent. So this is Mr. Joshua. I can see what's in the tail like that. So that's exactly what we want. So then the correct answer is 8 out of the total number, which will be 19. And then his reason for giving that is initially there were 20 people, 12 of which were women, 8 were men. These two make up the total population. But taking away one woman brings down the total to 19. But the men remain 8. The probability of picking a man now becomes 8/19. And since the woman's number reducing affected the men as well, then we say this is a dependent one. Remember, this only works for dependent probabilities, but for independent ones, it doesn't work. You will have to go through the trouble of applying the formula. And if you are lucky to realize that it's independent, you can, for the intersection, just multiply the two probabilities given, and then you find the intersection, and then you apply it to the formula. Okay. So I'll try to get a question that provides us with independent probabilities. Okay. So maybe I'll either refer to the slides. Yeah.
Mr. Prince,
Yes, sir.
can you please use the formula to simplify one of this example?
Oh, okay. So let's try that. Okay, that's a good suggestion. So which one should we pick? Should we pick the first or the second? Okay, let's pick the first and
The
maybe we'll do the
first one.
second after. All right, the first one. Okay, so then the question says that a box contains 2 yellow balls, 3 brown balls, and then 5 white stones. Stones. What? Stones, not balls. Okay. Now, if a white stone has been picked, what is the probability that the next one picked is yellow? So we are looking for the probability of picking a yellow stone, given that you first picked a white stone, like so. And then that will mean that we should know the probability of picking firstly a white stone and following it with a yellow one, and dividing that all by the probability of picking a white stone at all, a yellow stone at all, like so. That's y, by the way. Okay. So now let's define all the parameters. Probability of picking a yellow stone is going to be number of yellow stones over the total number of stones there. That's going to be, oh no, sorry. It's over W, not over Y. All right. Because the precondition is
Yeah.
white.
I wanted to do
Good.
for attention.
I almost messed up. All right, thank you. So then the probability of picking a white ball, let's first figure out what that one will be. That will be the total number of white balls over the total number of stones. Hey, over the total number of stones. So the total number of stones, the number of white stones is 5, and the total number of stones is what? 10. Now, probability of first picking, no, the probability of picking a white stone and following with a yellow stone. Let's figure that out. Okay. So then this will mean that we are picking stones that are white and yellow in a sense or something, or picking a stone that is white and follows a yellow stone. But since we started by picking a yellow stone, then it's supposed to be yellow first before white. Okay. So to find this intersection, we are going to look for the chance of whites, and yellow.
Hello, Mr. Prince. Hello, Mr. Prince. Please, are you there?
I think he's
Okay. Oh, he has muted himself.
maybe the network or something.
I want to ask him something. So, it's the network, I guess.
I think his network is not stable. So let's wait.
Yeah, he'll come back again.
Sorry, sorry guys. A call came in and I had to take it. Okay, sorry. Please, where were we?
Okay, Mr. Prince. Please, I want to ask you, but the
Oh,
Sparksman was saying that he will bring of the objects, the one that we've done for the IE and if I say
for the
the
quizzes and IE and
assignment.
yeah,
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 he said he will bring that one 25.
yeah.
Yeah, so is
I
that
believe
what
he
we
did
are
say
doing?
something like that.
Yeah,
Yeah.
he
So
said
yes,
something
I
like that.
have. I went through. I tried to get some. So I have not gotten the exact ones, but I do have some. I took some from sources, and I myself have gathered a
Oh,
few from what we have done. And currently, I have struck out the ones that are concerning conditional probabilities. And then I have
okay,
created similar questions, and then I've built on them using the
okay,
progress. So then you're starting from easy all the way to hard. So what we have been solving so far are just like the conditional probability questions that have ever appeared in some of the quizzes. I compiled a few.
okay. Then I'll try getting all for you then.
Oh, okay, please, if you can, that would be very great. That would be
Yeah,
very
I
great.
will.
Currently, I'm trying to gather from sources like an illegal miner, and I'm asking around to see if I can
Oh,
get it. Actually, I believe most of us will also be interested in that as well. All right,
yes.
that will be
So
very great. All right.
I will try and see if I can get it for you, but I'll get it for you. I promise that.
Right. That would be very wonderful. Thank you.
All right. So maybe
All right.
this evening you see it.
Oh, that's fast. Thank you. Thank you. Thank you in
You're
advance.
welcome.
All right.
Okay.
Okay. So where were we before the call came in, please? You need to share. Let me share. Sorry. Okay, yes, I believe Mr. Kayum or somebody mentioned that we should try working one of these problems using the formula, right? So then let's get to it. So then we picked this guy right here, and we said we were going to solve that. We are using 2 yellow, 3 brown, 5 white stones. We are supposed to find the probability that the first ball picked, the ball we are picking is yellow, given that the first one we initially picked is white. So yellow, given that the first is white. Good. All right. So then that formula will be probability of picking white intersection yellow, that's Y and W, over probability of picking white at all. So P of this over probability of picking white. Okay. So then the probability of picking white, we found that to be what? The number of whites there were, that is what? Exactly 5 over the total number of balls. So probability of whites over total number of balls. So that's going to be 5 out of 10 or 1 over 2. Let's use 5 out of 10 first. Now we look at the probability of picking white intersection yellow and how we can find that. So now if you want to use the formula, mind you, in this case, there is no logical way of picking a ball that is white and at the same time yellow because the question didn't state it. What this means is that we are going to use the formula to calculate intersections for dependent probabilities. For independent probabilities, it's just, if it's A and B, it's just the probability of A times that of B. However, for dependent probabilities, it is going to be probability of A times the new probability of B. Think back to the fact that in independent probabilities, both events do not affect each other. But for the dependent ones, if I pick a single white ball, it now affects my probability of picking a brown ball, a blue ball, or something, or a blue stone or something. So what this means is, the reason why we are doing this and we are not just going ahead to find the number of white balls that are at the same time yellow is that the question was specific and said there were 2 yellow balls, 3 brown balls, 5 white stones, stones. And none of these stones had 2 colors. Therefore, there is no common intersection between them that we can easily pull out. So in order to find the probability of getting a ball that is yellow and following it with a ball that is white, we are going to have to multiply the probability of picking a yellow ball by the probability of picking a white ball. But remember, if we first pick the white ball, it's going to affect the probability of picking a yellow ball. So then this is going to look something like this. First off, we pick the probability of getting a white ball because it says provided that the first one was white. So the probability of picking a white ball, we know that to be what? 5 out of 10. To find the intersection, we will multiply that 5 out of 10 over the new probability of picking a yellow. And what's the probability of picking a yellow after we've picked the whites? It's going to be the number of yellow balls, which is 2, all over the number of white balls, all over the total number of balls, which is 9. This is different from just going ahead to multiply A by B, which would have been 2 over 10 times 5 over 10. That would have been for independent events. But for dependent
Mr.
events, you
President,
realize that one, yes,
where is where from that night?
where from that 9.
Yeah.
Oh, okay, sorry. Let's go way back to the question, okay? We are picking, according to the question, a white ball first, a white stone first. Picking a white stone reduces the number of stones from 10 to 9, right?
Yeah. Yeah, I now
So,
understand.
so yeah, so we are saying if you first pick a white stone, that's 5 out of 10, that's the probability. And which is multiplication, you pick a yellow stone, which is 2 out of the remaining stones, 9. What you're going to end up with is 5 over 10 times 2 over 9. So the 5 over 10 is when you pick the first stone, which is white, and 2 over 9 is when you pick the second stone out of the 9 stones left, which is that's that. So 5 times 2 gives us what? 10. And then 10 times 9 gives us 90. And this will simplify to what? 1 over 9, right? But then I'd like to keep it as 10 over 90 for the sake of the calculation we are doing so that it will help us be faster. So let's plug these things into the formula. So now we know our probability of white intersection yellow. And that is what? 10 over 90. And we also know the probability of white is 5 over 10. So then the formula says we take our 10 over 90, that's white intersection yellow, right? So over 90. And we divide that by probability of picking a white, which is what? 5 out of 10, like so. So then let's go ahead and do the simplification. 10 over 90 simplifies to 1 over 9, right? And then 5 over 10 simplifies to 1 over 2. So if we rokoto it or if we reciprocate it, it becomes 2 over 1. Then you do your multiplication. 1 times 2 gives you what? 2. And 9 times 1 also gives you 9. Now, it was a drag and a waste of time, but in the end, it still brings us to the very same answer that we got when we just used our mental, like our minds, without penning it down on paper, which said that after taking the first ball, you'll be left with 9 balls, of which 2 are yellow. Therefore, your probability becomes 2 over 9, and you're done. So you see, we went a long way. Even while we were going the long way, we still came by this particular probability, which literally says that after you pick the first one, the blue balls are now going to be 2 over 9. Like it literally stated that. It stated the answer even before. It was foreshadowing, and then in the end, we get the same answer that we would have gotten even if we didn't apply the formula. So I believe you were having doubts that perhaps there might be some difference there, but then this is exactly what it is. And it can actually apply to every question we've solved so far because all the ones we looked at, I intentionally gave us independent ones so that we can look at them in this light. Okay, so yes, you can try applying the formula for the same second question. So now you try that. Apply the formula to the second question and see if it gives you the outcome that we want. That is what? 8 over 19. And if you have any questions, please go ahead and ask. Okay, we have come to the last slide of this section. So dependence probability and conditional probabilities, we can say a bye-bye to them for now until we look at Bayes' theorem and total probability. And then after I go through the detailed questions that Antivida will be providing, we will even be having more questions to tackle. So we'll be equipped with what we need for our end of SEM exam. Hopefully, I pray that the lecture doesn't do us a la school like the way Professor Solomon did to us and then gave us English for IT professionals, dubbed as mathematics.
Um, Prince, I have a question.
Yes, please.
Yeah, so concerning the probability W, the white intersection yellow.
Yes.
Okay. Yeah, so when you did the probability that is white, okay,
Yeah.
you did 5 over 10. But when
Yes,
you were
please.
doing the probability that is yellow, you did it 2 over
Yes.
9.
Yes,
Yeah,
please.
but from the question, it says if a
Yeah.
white stone has been picked. So why didn't
Yes.
we um, do the probability of white 4 over 9, but rather 5 over 10, and rather doing the probability of yellow 2 over 9?
Okay, that's a very good question. It's a good observation, and I'm glad you asked. Okay, I wouldn't have talked about it though, but I'm glad you asked. So now, think of it this way. We need to know the probability of first picking a wise ball and picking a yellow ball next, right? Because the question mentioned that the first ball picked was white. Is that clear? So we need to first know the probability of picking a white ball and picking a probability of picking a yellow ball. Remember that and is multiplication basically. So if we are starting from the white ball, probability of picking a white ball, before we pick a white ball, the number of balls in the bag is 10. So probability of picking a white ball is going to be 5/10 because we are starting with the white balls. But the condition says that after picking the white ball, we didn't replace it. So the white ball, yes, at the time when you were picking the white ball, its probability was 5 white balls over the total number of balls, that's 10. But after you picked one white ball out, you now alter the number of balls inside the bag, changing it from 10 to 9. This doesn't affect the white ball you've already picked because at the time you were picking it, its probability was 5/10. But now that you're moving on to the yellow ball, the total number of balls has dropped from 10 to 9. Therefore, you must alter the probability accordingly. So then it now becomes 2/9 for the second pick. But on the first pick, there were 10 balls. Mr. Desmond, does this make sense? On the first pick, there were 10 balls.
I get it. I get it
Uh-huh.
now.
But on the second one, there were 9. All right. So that's the reason why the first one we didn't alter it, but then second one we altered it to fit the fact that they have been reduced by 1 ball, 1 stone. Hey, why are we even talking about? I don't. Okay. So now with this, try with the second one and see if it gives you the same answer. Then we know that this particular strategy is foolproof, and no matter what you do, it can come in clutch for you when you come across dependence probability questions, provided you can think of the right things. Because if you think wrongly, everything will just, it will swerve you. Okay, so let's do the working for the second one. Or you are working it. Are you working it? I don't know if you're working it or not. If you're working it, then you just tell us, oh, it was the same, it wasn't the same, and then we go to the last slide for a summary. Then we can call it a nice day. Okay, let's work it, please. So we first find what we need. In this case, it's just women and men, so there is no confusion. It says we are first picking a woman and followed by a man. So to first pick a woman, the intersection for these two. So we need, remember the denominator is going to be probability of W, right? And the numerator is going to be probability of men intersection women. Because we are trying to see the probability of picking a man, given that the first pick was a woman, like in the formula like this. So let's first find the probability of men intersection women. So then, just like the other questions, there is nothing here that says there is a man who is at the same time a woman. So for that reason, you cannot get a number of people who happen to be men and women at the same time. And then, therefore, we have to just find the probability of picking a man, multiply that by the probability of picking a woman. Remember that we picked the woman first. When we were picking the woman, there were 20 people in the class. So the probability of picking a woman at that time was 12/20. But after picking the woman, it reduces the total number of people in the class from 20 to 19. Therefore, the probability of picking a man becomes total number of men, which is 8, divided by the total number of people, which is 19. And you can see already that this actually foreshadows the answer, the 8 over 19, because it literally says the probability of picking a man, and which happens to be the same question that the same thing the question is asking. What is the probability that the second person chosen is a man? You see that? But let's still solve it anyway. So let's simplify so that it makes working easier. So 2 goes here 6, 2 goes here 10, 2 goes here 5, 2 goes here 3. So 3 8 is 24. And what's 5 times 19? What's half of 19? Say 9.5. So 95. So then this gives us 24 over 95. That's the probability of men intersection. Why am I using B here? I think it's meant to be W, women. So probability of men intersection women is 24 over 95. After finding this, we can now plug that into the formula. So the probability of finding men intersection women is 24 over 95. Let me just do it here. We divide that by the probability of finding a woman, which was given as what? 12 out of 20. So then you can even see from the working that the 12 out of 20 will cancel the initial 12 out of 20 that was used in the working. And as it does that, it eliminates the 12 out of 20 from the 24 over 95, and it will leave you with 8 over 19. And that's why you always return to the same answer. So punch it on the calculator, do 24 over 95 divided by 12 out of 20. 24 over 95. 12 out of 20, we reciprocate it and it becomes times 20 out of what? 12, like so. 12 goes here 1, 12 goes here 2. 5 goes here 18 times. 5 goes here. That was 18 or not 10. 5 goes here 4 times. 2 also goes here, the car. And then 2 goes here. How many times? 9 times. Okay, am I missing something? 9. This multiplication doesn't give us our desired value. 1 times 4 does give 4, yes. But then our denominator is 9. Perhaps a problem with my working. But please, when you punch this on the calculator, what was your answer?
No, you get 8 over 19.
So I am the one who is fooling around then. Oh, okay. Okay. So then 8 over 19. All right. So then let me see that. 24 divided by 95 or over 95, and we are dividing that by 12 over 20. Yeah, that's right. So 8 out of 19. 8 out of 19. Okay. So we have come to the end of today's session. Today's session's aim was to further develop what we had learned concerning conditional probabilities. And I believe that by the end of this lesson, even if it was already clear to you, it has become even clearer, especially how to apply it to dependent events. Remember, if you are dealing with independent events, like in the case of tossing a die, mostly, right? Then one event is not dependent on the other. Therefore, there is nothing that is stopping you from finding the intersection by just multiplying both events. So like in the case of the first question when we're dealing with the Ludo die, you could have actually found the intersection just by multiplying both events in question and then simplifying it. That would have given you the intersection you were looking for. Alternatively, you could have just done what we did and then counted how many possible events we are looking at, described as the intersection, and that is very easy to do. All right, let's move on to the last slide. What have we learned today? Probability measures how likely events are. Events and outcomes are the building blocks of conditional probability, and it looks, building blocks Events and outcomes are the building blocks of probability. Sorry. Conditional probability looks at the chance of one event given another has already happened. Everyday situations often involve conditional probability. We can use a simple formula to calculate these probabilities. And that probability is the probability of events A given B equal to probability of A intersection B all over probability of B. We can use conditional probability helps us make better decisions in real life. So information for you is I've prepared slides just like these ones tailored for our lessons. So as Sister Ivan keeps saying, honestly, you are getting more than you are paying for. So I will plead with you all, do your best to settle your debts. As you can attest, the lessons before this, UGBS, DCIT 104, they were actually helpful in the examinations. The tutors have not been settled. So please let them earn their time's worth. Okay. So the payments that are left to be made, we hope that by the end of this week, now all the big men and big women here once settle in Abibia IFA. Amen. We've come to the end of our lesson. If you have any good questions, please ask. If not, we call it a night and then see you tomorrow. Goodbye, people.